thanks to the organizers for allowing me to talk here, and also thanks to the previous speakers, and especially Elias and Guido for setting me up with a really nice introduction. So today I'll be talking about some of our recent findings on Lyman-α emitting galaxies in the very first stages of galaxy evolution with JWST, and how that may look as we go to the ELT era. And so this is work done mainly with the JWST collaboration. So just to quickly introduce what this survey is. This is a collaboration between the NIRCam and NIRSpec GTO teams. And we've now taken nearly all of our data. And so I encourage all of you to go and check out our pretty much fully publicly available data releases. And here is some nice examples of some of the very deep imaging we've taken over the goods fields, and also all of the galaxies that we get very deep NIRSpec spectra for. And yeah, as I mentioned, this is done using NIRCam imaging. So we select galaxies from very deep new imaging, and also some HST pre-imaging over the goods fields. And just to give you some numbers, so we have several sources with over 100 hours combined of NIRSpec data. So these are really some of the deepest JWST data that are available currently. So, of course, as we are now delving into the JWST data, we're really able to probe this very fundamental reionization epoch, where a lot of the foundations were laid for the rest of cosmic history. And so I'm going to be focusing here as well on this process of reionization and what we can learn about it using Lyman-α emitting galaxies. So when we talk about cosmic reionization, usually this is the kind of framework we try to think of. So as we discussed just before, we're trying to count the number of ionizing photons that are being emitted by these galaxies. So basically that requires 3 steps. First of all, we have to know how much photons are being produced. And so that's basically this UV luminosity density times some efficiency factor. And then, of course, those photons have to leave the galaxy and reach the IGM. So you might think of a picture like this, where the stellar population is producing those ionizing photons. They leak out of the galaxy in certain sight lines, and they ionize the neutral IGM. That's a very simplistic galaxy-centric picture. Then, of course, at the end of the day, we do have to go in with simulations to precisely calculate, for example, how much hydrogen recombines in the IGM. But all in all, we do know that by redshift 6, so within 1 billion years of time, the entire universe has been reionized. So somehow these first galaxies have to be very efficient at producing and also leaking ionizing photons. So what can we learn about this process through Lyman-α? Well, this is just a schematic from a paper by Charlotte Mason. And here it's showing you, basically, depending on where your galaxy is sitting relative to this ionization front. So if it's in an ionized bubble or out of it, that will drastically impact what your Lyman-α profile will look like, what we see when we take a spectrum of this galaxy. And you see, even in the most extreme case, the IGM transmission actually impacts your spectrum well beyond the wavelength of Lyman-α. And so what we see then observationally is that beyond the redshift of 6, basically there's very, very few galaxies that emit any Lyman-α photons. And this has been known for a long time. And what's more, we are now actually picking up with JWST some of these very extreme galaxies, mostly beyond redshift 10, where we see this very smooth turnover around the Lyman-α break. And so this is pointing out that there must be actually not just the IGM, but really very dense neutral gas sitting around these galaxies. So then taking all of that into consideration, then it was actually a very big surprise when we took a spectrum of one of the, well, the highest redshift galaxy known from the HST era, which is GNZ11, and we actually found it had Lyman-α emission. So that's very surprising. How is that possible? Well, one thing you can see there is that it's actually been redshifted up to 500 kilometers per second. And it turns out that might be enough for the Lyman-α photons to escape, even if the IGM is fully neutral. But what I'm going to be talking about here is our full JADE sample, and in particular, these 3 redshift greater than 8 Lyman-α emitters out of the full sample. So before JWST, there were only about 2 galaxies which were known Lyman-α emitters above redshift 8 that were very robustly found. And so now we've picked up 3 more looking at these very much fainter galaxies. And so potentially we're probing further back into this process of reionization and perhaps some kind of small early ionized bubbles. So with NIRSpec, of course, we don't just see the Lyman-α line, we actually see the whole range going all the way from Lyman-α out to some of the rest frame optical lines. And you can see an example here. We probe many, many different emission lines, and so we can really dig into some of the physics of these Lyman-α emitters. And what we see is that they have very, very strong nebular emission. You can see that from the strong lines, but also this Balmer jump feature, which is showing that there's just a lot of ionizing photons being reprocessed within these galaxies. What's also interesting is that some of the UV lines that you can see there are actually remarkably strong. So normal galaxies almost never show these very high ionization lines like carbon-4, and this is showing us that they're actually exhibiting very, very hard ionizing radiation fields. If we look at the stellar properties, so these galaxies, perhaps unsurprisingly, are quite low mass, and they all show this very strong upturn in their star formation history. So they're very, very experiencing a very strong starburst only in the last maybe 5 or 10 megayears. And what's also interesting to point out is that when we look at the imaging, actually, most of them seem to be accompanied by these very nearby sources, which are too faint to robustly say if they're the same redshift, but it's very possible. And these could be satellite galaxies, meaning that the whole system is maybe undergoing a merger, which might spark this star formation, which is something Callum has been working on. And we've mentioned a little bit this problem of AGN in these very early galaxies. What we can say, so it's not completely clear, and of course we are only look at 3 Lyman-α emitters here, but actually the strongest out of those 3, if you look at some of the rest frame UV lines, we see that it's completely consistent with star formation. So there might be evidence for some AGN activity, but at least the very strongest one is very clearly a star-forming galaxy. Okay, what I thought was very remarkable is when you plot the strength of the Lyman-α line, so that's shown on the y-axis here as the equivalent width, and you compare it to the star formation rate surface density, you see that there's this very strong correlation, both in local sources, but also these 3 high redshift Lyman-α emitters. And especially that very strong Lyman-α emitter shows a surface density that's just well beyond anything we can see locally. So these local galaxies are already very extreme among their contemporaries, but so at this high redshift, we're really seeing a completely different mode of star formation. Okay, so in the final bit here, I just want to point out that using the Lyman-α properties, we can actually start to work out what their ionized bubbles look like. And so here I'm plotting just their distributions spatially and along the line of sight, so you can start to probe their environment and see which galaxies might be responsible for creating these bubbles. So you see the dashed lines there showing some of the ionized bubbles. There are indications that they live in somewhat overdense environments, and so they might have some help from nearby galaxies in creating these ionized regions. But in the most extreme case, which is on the left, the size of the ionized bubble, doesn't even fit on the plot here. It's so big that there seems to be some kind of inconsistency there about how the Lyman-α is able to escape, and being able to we're being able to observe such a strong Lyman-α line. So in terms of looking to the future, so here these are 100-hour combined observations with JWST. One thing that really is lacking at the moment is high resolution spectroscopy. So you can see in the bottom plot there, the very peaked dashed line, that's the intrinsic profile of Lyman-α, or at least what we think it looks like, but it's being smeared out just because the relatively low resolution of the NIRSpec instrument doesn't allow us to measure this profile. And so this is, I think, really an ideal science case for the next generation of telescopes, and in particular, ELT and Mosaic will be able to look at some of these sources and within about 10 hours get a much higher resolution spectrum for many of these sources. And this is very important because it'll really teach us how the Lyman-α is being able to escape out of these galaxies and tell us about their ionized regions. So I'll finish up here to say that Lyman-α has been a very powerful tool to learn about reionization, but it continues to do so as we get more data with JWST, and I think it will remain to do so as we move to the ELT. And I'll stop in a second just to say that there's some more very exciting work coming in this space. So thank you.
Thank you. Do we have a question? Yeah.
Thanks. Great talk. I'm interested in what you said about that generally compact galaxies that helps Lyman-α escape. What do you think is the reason for that, and is that something that we see at lower redshift?
So yeah, just to reiterate that just because of how compact they are, the surface densities we see just aren't comparable with anything we see in the local universe. So in a way, this is the first time we're learning about it, and I do think it really ties in together with the leakage of Lyman-α and ionizing photons more generally. You can imagine the more compact a galaxy, the more effective the feedback is in blowing out some of the gas and dust that allows that escape to happen.
Rather than outflows being more important, for example?
Well, I think it ties into the same thing. So your outflows are able to displace more material perhaps when they're in a more compact configuration. Yeah.
Thank you.
Okay, that's very short then. Okay.
Apparently it's working, kind of. Touch it. Okay, then no touching the antenna, everyone. So very much on the same theme, just to make sure that we've established all the effects. So the outflows can help to carve out a low density zone, but the velocity, the bulk flow can also help, right? So you don't just have to identify a spatially empty or ionized zone. The velocity will help to make the Lyman-α line appeared. So have you taken that into account, the velocity offsets? Because you seem to be talking about spatial area.
Yeah. So this is something we have looked at. So even though we're, the spectra on super high resolution, you can measure the peak of the line quite well. And so that's something we take into account when we're working out, for example, what the ionized bubble needs to be when the Lyman-α escapes through the IGM. So yeah, that is something we can already do. Yeah.
Okay, let's thank the speaker again, and then we can move on. So the next, can you stop sharing, please? Yes, so the next speaker is Maxime Taras, who is going to talk about toward quiescence, the role of optically faint galaxy in galaxy evolution at high redshift. Try to use the other microphone, this one. Yeah.
Hello. Yeah. Can we hear me or not?
Or you can try this one. It's up to you. Don't touch the antenna. Don't touch the antenna. Move. Yes. Like
yeah.